Hi guys, just thought I'd go over a quick intro to compound bonding. Now, we've done lots of bonding in the elements. Pretty much a lot of this is revision, but there's one or two sort of wee things as you see as we go along. So learning outcomes are in the first two slides. Here's just a wee quick recap on covalent bonding in compounds from last year. Now you know by ionic, it has to be a metal and a non-metal, and it's a transfer of electrons forming ions. Metallic bonding, that happens in metal elements. Obviously, that's to do with elements, so we don't need to look at that too much in compounds. And then covalent. Now, covalent is where it gets a little bit more complicated and higher. There are two types of covalent bonding: pure or non-polar covalent, and polar covalent. Now, polar is also to do with our differences of electronegativities, as you'll see as we go down these slides. So, quick recap from National 5, you know what a covalent bond is. It's a shared pair of electrons between two metal atoms. How is that held together? It's held together by the two positive nuclei, the protons in the two positive nuclei, and their attraction, the electrostatic attraction between the protons and the shared pair of electrons. So, little recap again. Obviously, covalent bonding happens in molecules and networks. Molecules are known as covalent molecules or sometimes discrete molecules. They're always solid, liquid, and gas at room temperature, whereas networks are usually solids. So if you look at solids, you can form that on a piece of paper if you want. The answers are obviously coming up. They've both got the same 4 outer electrons. So in that case, they both can form 4 bonds, and it's a complete network. So a network is you've only got strong covalent bonds, very strong covalent bonds, so therefore lots of them, very high melting and boiling points with all of these guys here. Okay, so that's pretty much all revision. There's not a lot of new stuff with the network. Ionic compounds, same idea, just this used to be a wee video. It doesn't work in these Google Slides, unfortunately. Ionic compounds, we're just going about the transfer. You've got the strong bonds and you've got an awful lot of them. Again, very high melting and boiling points. What we are interested in is still just looking at, when elements become ions, and what happens to the radius of the ion. So obviously if you lose a whole outer shell, you're going to get a lot smaller. If you're just gaining an electron, it's not going to make much difference with the shell. So this is what these questions are using, so similar to last time, looking still at the trends of ionic and ionic radius compared to the atom's radius. Okay, that's a question on the worksheet. Now, back to covalent bonding. Now, this only works if you do present mode. So if we present it, you'll see that that's the standard covalent bond there. And you've got, obviously, they're all 1 to 2 full outer shell. And then there's various ones telling you the information through that. So please play that as a presentation. Now, that's all very well with the normal covalent bond. Now, the problem is what happens when that share of electrons is unequal. So let's say one atom has more pulling power than the other atom. So back to electronegativities that we looked at last time. So we know fluorine has a high electronegativity and hydrogen has a low one. So if we look at hydrogen fluoride, that has a higher pulling power. So the pair of electrons is going to go towards the fluorine, making the fluorine slightly negative and making the hydrogen slightly positive. So how you write that is delta negative and the hydrogen becomes delta positive. Okay, so there's a pole now. Okay, so that's why these are called a polar bond, polar covalent bond, and this would be a polar molecule. But don't worry about that too much because we'll go into that next time, but just note that it's a polar bond. Okay, so that's all explained here, and looking at the electrons. Stronger pull for the fluorine, So therefore the fluorine becomes negative because it's got a stronger share of those electrons as opposed to the hydrogen. And then electronegativity we looked at last time, so you can revise that going through. All we're looking at here now is, what's the difference in electronegativity. So if you look up the electronegativities, that is obviously on your data booklet, page 11. Look at the difference between carbon and chlorine. Carbon is 2.5 and chlorine is 3. So the difference is 0.5. Okay, 0.5 is quite low, but there is a difference. Now, how do you know the difference between something that's going to be polar or non-polar? So you've got to sort of think about it. It's not a complete, like, dead start lines. So it's called the bond continuum. So you've got your non-polar all the way up to your ionic. So non-polar, you're talking like probably under 0.4. Around the 0.4 mark, I think I've written it here. Yeah, around the 0.4 mark. If your difference of electronegativity is less than 0.4, 0.4, you're going to be non-polar or pure covalent. If you're around the 0.4 to 1.5 or 6 and you don't have any metals in you, you're going to be polar. And then obviously ionic, you're going to have a metal in there, and your difference of electronegativity is going to be above 1.7. Now, there is a fun little video here you can watch, sing along to if you want, but let's look at that. It is not an absolute law. Okay, so there's a murky business between 0.4, around the 0.4, don't know whether it's polar or non-polar. They're never going to give you one that's a bit dodgy. It's obviously above 0.4 or below 0.4. As again with the ionic. Now, it's the problem with the ionic, obviously there's issues with transition metals. So when you have a look at this one, titanium chloride, tetrachloride, well, it's a gas at room temperature. But wait a minute, all ionics are solid. So we need to explain that. So have a think about that. That obviously this has high tendencies to be a polar covalent bond molecule, which we will look at a little bit later in our next topic. So have a go. Go through the worksheets. The worksheets here, it's called Bonding in Compounds. Before, I forgot to mention, before you get started, obviously do the starter task from last time. It's a wee quiz about elements and bonding and that. Okay, give me a shout if there's anybody stuck with anything. Good luck. Bye.